In this video, we're going to work through some practice problems with area and volume as they show up in a pretty standard calculus class, but especially for those of you who may be taking the AP exam. The area of volume question is traditionally a free response question we see. And so I definitely want you to be prepared for that. We're just going to take a look at a few practice problems. Now, I am going to focus on setting up the integrals for these problems, and I will use a graphing calculator to be able to get the answer. If you want to work through the actual antiderivatives, that is totally fine. That's just not the purpose of this video. So just know that that's how I'm going to focus on setting up the integrals. That being said, if this is the first time you're seeing my face, hi there. My name is Dr. Marissa May. I am on a mission to help students feel confident in their math class. So this video, with all videos that are on my YouTube channel, as well as resources that I provide like learning guides and tutoring sessions and tools, are meant to help empower the student to feel confident in their math class. So if you have a question or concern or something that I can help with, please feel free to leave me a comment below. Also, I'm putting my social media handles on the description. That way, if you want to reach out to me, send me a DM. That would be great. Well, let's jump right in. Let's see, we're looking at the region bounded by the ln of x, grabbing a highlighter here, the ln of x and the line x minus 2. We want to be sure we can use a calculator to show our answer, but we want to show the integral. So we want to find the coordinates where the two graphs intersect each other. So that is where we are taking the two equations and we're setting them equal to each other. Ln of x equals x minus 2. Now, when you go to a graphing calculator, this is where you're going to look for the intersection of these two. So I'm going to put ln of x and y1, x minus 2 and y2. I'll find that intersection. Now that we have both of those solutions, let's go ahead and write the integral for the area. So we have our first intersection point there, our second intersection point there. I'm going to do our integral in terms of x. So our integral is going to go from 0.159 to 3.146. We're going to do the top curve minus the bottom curve. So the top curve here is the ln of x. And then minus, be sure and use a parentheses around the x minus 2 dx. Now again, we can put this in the graphing calculator to get the answer. And we get 1.949. Now, in problem number 2, we're going to take this region, revolve it about the line y equals -3. So that line is down here. If you saw my previous video, you know that we talked about the big radius and the small radius. So the big radius here is from the axis we're rotating about all the way to the furthest curve. So that big radius, I'm going to call it capital R, is the ln of x minus -3, or just the ln of x plus 3. And then that small radius is going to go from the axis of rotation to the closest curve, which would be the line there. So that's going to be the line, oops, it's minus 2, minus a -3. So that's going to be x plus 1. So when we write this integral, we have our pi on the outside, we have our bounds 0.159 and 3.146. And then we have our big radius squared, it's our ln of x plus 3, minus our small radius squared, that's our x plus 1. And then again, we can put this in our graphing calculator to find the value. And for this one, I get 10.886 pi. Now, if you saw my previous video, you know my biggest tip on this is to integrate without the pi in it. Just do your integral in your calculator and then stick the pi on your answer. Because your graphing calculator will give you a fraction if it's possible, but if you put the pi in it, it will not. Okay. All right. Number 3, then write and evaluate an integral expression that can be used to find the volume of the solid generated when r is rotated about the y-axis. So this time we're going around a vertical axis and we are going to have to integrate with respect to y. Okay, that means we're going back to our curves and we're solving for x. And we get that x equals y plus 2. We get that x equals e to the y. Okay, so everything in my integral is now going to be in terms of y. So when I do my big radius, we are coming from the axis we're rotating about to the furthest curve. That's the line this time. Y plus 2 minus 0, which would be y plus 2. When I do my small radius, then I come from the axis I'm rotating about to the closest curve, which is my e to the y. So that is e to the y minus 0. We get e to the y. So let's write our integral, again, in terms of y this time. And so we are going to use the y values for our bounds. So it's negative 1.841 and 1.146. Big radius squared minus little radius squared and dy. Okay, let's put these in our graphing calculator. And I get 5.443 pi. So remember your big radius, your small radius, those are going to be key as you try to write these integrals. Let's look at a new region this time. This time we have f and g, f of x being 1/4 sine of pi x, g of x being 4 to the negative x. And we're only looking at the region in the first quadrant. So notice that R is bounded in the first quadrant by the y-axis and the two curves, and then S is bounded just by the two curves. Okay, so we want to find the points of intersection first. Again, this is where you're going to set these two equal to each other. You're going to put them in your calculator and find those points of intersection. And for those, I get 0.178.781. And then I get 1 and 0.25. Okay, now we want to find the area bounded by the graphs of f of g and the x-axis. Sorry, by the graphs of f and g and I think this should be the y-axis here. So we want to find the region R. Okay, so we're going to go from 0 to the first intersection point, 0 to 0.178. And notice that that g of x is on top on this region. So we're going to do g of x, which is 4 minus x, minus f of x. Watch your parentheses again. And dx. Let's see what we get for that. And I get 0.065 for that piece. And that's finding region R there. All right, let's take region R and revolve about the line y equals 8. Now y equals 8 is going to be up here. So when we do our axis of rotation, remember we're rotating only region R. So our big radius is going to go from the axis we're rotating about to the furthest curve, which is going to be f of x. So my big radius is f of x minus 8. And then my small radius is going to go from the axis we're rotating about to the closest curve. So that small radius would be g of x minus 8. And so I would write this as an integral. My bounds are for the region of R, which are 0 and 0.178. And then I have my big radius squared minus my small radius squared. And let's see what we get for that integral. And for that one, I get 0.948 pi. Now, notice in problem 5, now we're going to rotate region S, and we're rotating about the line y equals -1. So this time when we do our big radius, we're coming from the axis we're rotating about, but the furthest curve is the f of x curve. So this time our big radius is f of x minus -1, which would just be f of x plus 1. And then our small radius is going to be from the axis we're rotating about to the inner curve. That's going to be g of x. So that's going to be g of x minus -1 or g of x plus 1. Okay, so let's write that integral. That is pi times the integral from 0 to 0.178 of my big radius, that's f of x plus 1 squared, minus my smaller radius, that's g of x plus 1 squared dx. And let's see what we get for that integral. As I was putting this in my calculator, I discovered the bounds are wrong. These bounds are for region R. So I need to fix them for region S. And so that's from the first intersection point to the second. And so that would be a 1 there. Okay, so that gives me 1.451 pi. So I hope this is helping you see how we can take different regions. You'll be expected to do area, find the intersections, revolve about a certain axis. There are two AP problems that I do recommend, and I will link the solutions below in the description. So you got the 2012 question number 2 is a good one to practice with on this topic, as well as the 2013 question number 5. So I will link those the solutions below so that you have them. Also, thanks so much for watching, and don't forget to hit that like and subscribe button. That way you get a notification every time a new video is posted. Thanks so much. Bye-bye.